Hi, this video is about acceleration vectors. It's keyed to University Physics by Young and Friedman, although any physics textbook is going to deal with this fairly early in the course. We talked in the previous chapter, chapter 2, about acceleration in a straight line. The difference between, of course, that kind of discussion of acceleration and the kind of acceleration we're talking about here is that here we want to talk about acceleration as a vector. Remember, a vector has direction. So we can talk about, I'm increasing speed at a certain, and acceleration in that sense. But if we want to talk about increasing my velocity in a certain direction, then we're talking about vectors. Now, a lot of the stuff in this section, and this is section 2 of chapter 3 in this particular physics book, is an extension of the first section, which was on position and velocity. And so basically, the first two slides I have here are basically taking the same formulas and the same ideas of section 1 and simply applying it in relation to acceleration. Previous video talked about it in terms of velocity. This video talks about it in terms of acceleration. And so if at any point you're not quite sure what I'm talking about, go back to that first video on 3.1 and watch it, and then come back and watch this again. So, for example, the average acceleration in a particular direction is going to be the difference in velocity divided by the difference in time. So the change in velocity divided by the change in time in a particular direction. The arrow over the top tells you that we're talking vectors. We're talking about acceleration in a direction or velocity in a certain direction. And so that's pretty straightforward. Acceleration is the change in velocity per time, right? So we can then say that the instantaneous acceleration is the limit as the change in time approaches 0 of the change in velocity divided by the change in time. This is basic calculus. We call this dv dt. The instantaneous rate of change of velocity per time is the acceleration. So the difference between the first formula and the second formula is the first one is approximate, while the second one is precise down to the moment. Okay? Little calculus that if you know any calculus, this is like right at the beginning of calculus. We can also take the kind of unit vector notation. We did this in 3.1 in relation to velocity. So if we kind of separate out the change in velocity in the x direction, and we separate out the change in velocity in the y direction, and we separate out the change in velocity in the z direction, if we kind of separate those out, then we can also describe the instantaneous acceleration, that is the instantaneous rate of change of velocity per time. We can separate it out in terms of the x direction, y direction, and z direction. And again, there's a video on unit vectors back in my chapter 1 materials, and I review it in section 1 of this chapter in relation to velocity. But basically, all the I means here is going in the x direction, and all the j means is going in the y direction, and all the k means is going in the z direction. And so we've just separated out the components of the velocity as a vector by x, y, and z in this last one. Again, all of this is the same as the first section of this chapter. I'm just now talking about acceleration as opposed to just velocity. So those are the vector components. The x component of acceleration is the instantaneous rate of change of velocity in the x direction. And the acceleration in the y direction is the instantaneous rate of change of velocity in the y direction. And the instantaneous rate of change, the acceleration in the z direction is the instantaneous rate of change of velocity in the z direction. Now, if you're just talking about something in 2 dimensions, you might not have a z. Z might be az might be 0 because vz is 0, because the position change is 0. So I'm just setting it up for 3 dimensions, but you could take away one of these if you're only in 2 dimensions. Now, because we're now talking about acceleration, you'll remember that velocity is the instantaneous rate of change of position, and acceleration is the instantaneous rate of change of velocity. But you can also say that the acceleration is the second derivative of the change of velocity, of position. So the x component of acceleration is the second derivative of the change of position per time in the x direction. And the y component of acceleration is also the second derivative of the change of position in relation to time in the y direction. And the z component of acceleration is the second derivative of the change of z position in relation to time. Again, this follows naturally on the fact that acceleration is the second derivative of position change. Okay, so we can also apply some of the formulas that we had in the previous chapter. I didn't do the angle here. It would be very similar to what we did in the last to figure out what the angle of an acceleration is. But if we basically take the acceleration of the components of acceleration and square them and add them, and then take the square root of that, then you're going to get the quantity, the magnitude of the resultant acceleration. This is a squared plus b squared equals c squared. Straightforward Pythagorean kinds of things. Okay, so all of that, everything that I just did is basically taking the same principles of the first section of this chapter and applying them to acceleration now. But now that we're talking about acceleration, it's appropriate for us to begin to talk about motion in a curve, motion on a curve. We haven't talked about that yet in this. Now, remember, velocity is not just speed, but velocity is speed in a direction. Okay? Speed is when we're just talking about, oh, I was going 5 miles an hour. That's speed. But if I want to say I was going 5 miles per hour north, then I'm talking about velocity. So velocity, by the very definition, includes a component of direction. So if velocity is not just speed, but also speed with direction, then whenever you change direction, you are changing the velocity. Just take a second to soak that in. If velocity, by definition, includes the matter of direction, then any time you change direction, then by definition, you are changing velocity. Now, what is a change in velocity? Well, by definition, a change of velocity is called acceleration. Therefore, anything that follows a curved path, because it is changing direction, is accelerating by definition. Again, read this PowerPoint slide again, or rewind it if you need to. This all follows by nature of the definitions of things. If velocity is direction, then any change of direction is a change of velocity, and a change of velocity is acceleration. Therefore, anything on a curved path is by definition accelerating in some way. Now, remember, in physics, acceleration doesn't just mean getting faster. It can mean getting slower, and in this case, it means changing the matrix of direction. Okay, so let's look at this, and there's some much better diagrams in any book, basically, you'll find. But for whatever reason, my picture ended up blurry. I apologize. So I've drawn a instantaneous velocity, v1, at a particular point of a dotted curved path here. And then I've drawn another arrow for an instantaneous rate of change of the velocity at another point. So I've called one v1 and the other v2. Now, off to the right here is basically I've used vector addition, or in this case it turns out to be vector subtraction, to figure out the difference, the change in velocity between v1 and v2. You can see in this diagram the little arrow that is delta v. That is, just using graphics, the change in velocity between v1 and v2. Now, let me break down that delta v into a triangle. And I initially wrote these wrong. I tried to correct them. So you have a negative vx component to that, or I'm sorry, it's going to look like this for you. So you have a negative vy, a negative vy component to this change in velocity, but you have a positive vx in this breakdown of the delta v. And so you can see that there's some acceleration going on here, right? You have a negative acceleration with regard to the y component of velocity, but you have a positive acceleration with regard to the change in the x component of velocity. Okay, so you can see, even right here, you can see the the way that there is an acceleration involved. And if you go back to the original diagram, you can see that that acceleration coming off of the curve, kind of pointing inward, that is in keeping with the change in velocity, isn't it? The change in velocity is generally pointing downward, and so we're not surprised to find that the acceleration is pointing inward. We call this, it's related to centripetal kinds of things. Okay, more on that in a later chapter. So let's talk about the components of acceleration and how they function. So the parallel component of acceleration is the part of the acceleration that's going in the same direction as the velocity. It's parallel, as it were, to the direction of the velocity. Now, if that acceleration is in that parallel direction, then we're going to get a change in the speed of that particle as it goes around the curve. The component of acceleration that is parallel to the path of the particle, however direction it's going, that's going to tell us about whether the particle is speeding up or slowing down. But the perpendicular part of the acceleration is going to tell us about the change in direction. Whenever a particle or something is moving on a curve, it is accelerating inward, is what we saw from the previous diagram. So the perpendicular component of acceleration is what changes the particle's direction of motion, whereas the parallel part of the acceleration is what changes the particle's speed if its speed is changing. By definition, its velocity is changing because of direction, but it may have a constant speed as it moves in a curved path. And so there'll be a positive acceleration in the parallel to the path if it's speeding up as it goes on the curve or whatever. If it's remaining the same, then it will have a zero acceleration parallel to the path of the particle. Okay, I hope that made sense. Rewind and watch it again if it didn't. Okay, so if speed is constant on a curved path, now velocity is changing by definition because it involves direction, but in terms of speed, if the speed is constant of a particle on a curved path, then the net acceleration is going to be exactly perpendicular to the path because there's not going to be any parallel acceleration or deceleration. But if the speed is increasing, that means that the net acceleration is ahead of that perpendicular. It's a little bit ahead of it. There's a positive part parallel that is therefore combining with the perpendicular part to be a little bit ahead of the perpendicular. If the speed is decreasing, that means it has a negative acceleration parallel to the path, and so its resultant acceleration is going to be a little bit behind the perpendicular. Again, Young and Freeman has a great diagram illustration of this in there. Well, now it's getting a little bit trickier, isn't it? This acceleration as it relates to curved motion. But we're not done. There's much to do before you're done with this textbook on motion in a curve. So, this has been acceleration from a vector perspective.